Let's discuss the nature of matter at an atomic level. I want to start by addressing this question: what is an atom? I mentioned in an earlier video that I like to do an internet search on these words, and I focus on the images that pop up. It gives me a quick view of what the internet thinks the definition of the word is. So when I did that, the first 20 or 30 images popped up and they looked a lot like this. Now this was the coolest looking one, the most artistic, but they all more or less had the same form. The simpler, more common version is just like this. When I was growing up, I actually remember learning this in elementary school. This was how we represented atoms. So you have electrons out here orbiting on the outside, and then inside you'll have protons and neutrons, and those cluster together in the inside, and that cluster forms the nucleus of the atom. This isn't a bad model in some ways because it's simple and it's easy to remember, and it connects with things that we already have in our mind, like planets going around a sun. But it turns out we don't teach this anymore, at least we're not supposed to be teaching this anymore, because it doesn't accurately represent our current understanding of how atoms work and how they're actually structured. So let's look at a more modern view of an atom. This model looks more simple, but it's more accurate. We don't view electrons as solid particles that are following definite orbits, sort of like planets going around a star. We think of electrons more as this hazy, cloudy, negative charge. Instead of solid particles, it's a distribution of charge. So the electrons kind of make up that cloud. In the center, we still have our very dense, positively charged nucleus where the protons and neutrons would be. I want to point out this number over here. The size of an atom is about 10 to the minus 10 meters. That's known as 1 angstrom. So that's like taking a meter stick and dividing it by 10 billion. So that's really, really small. It's actually 1,000,000 times smaller than the width of a human hair. So if you were to stand a human hair up, think of maybe this as a human hair, you could line up 1,000,000 atoms widthwise to equal the width of one hair. So that tells you that these are really, really, really small objects. What actually holds an atom together? It's something called the electric force, and I'll just do my best to give you a quick, simple definition of this. So here I'm trying to show a positive charge and a negative charge. Think of it as a proton and electron if you want to. The lines in between them are known as electric fields, and you don't need to worry too much about that. I just like showing it because it kind of makes it look like they're almost holding hands. Well, the point is that if you have two opposite charges close by, they will attract each other. So this is the phrase opposites attract, opposite charges attract. If you take this two similar charges, like two positive protons here, notice how the electric field lines are shying away from each other. They're repulsed by each other. So we say that like charges repel, and it's not just positive charges, the two negative charges would do the same thing. Right? These lines kind of make sense because there's actual pictures that look like this. So in this case, there's two electrodes. These are just basically metal points that have been charged, and in this case they're oppositely charged. And then they're suspended in a fluid, and they sprinkle, I think in this case it was pepper flakes. So they sprinkled them all around, and the pepper flakes naturally line up in this pattern. So you can kind of visualize the electric fields in this way. Over here we have two equally charged electrodes, and you can see how they're repelling each other, and here they tend to shy away from each other. In this case, I think they were using grass seeds. Anyway, the connection I'm trying to make is that for an atom, the negatively charged electron cloud is going to be attracted to the positively charged nucleus, and that's basically what keeps the atom as a whole together. I don't know if you read this text up here, but I wanted to highlight that it says the nucleus is exaggerated in size for clarity. Okay, when they say exaggerated, they really mean exaggerated. The nucleus here compared to the atom, the electron cloud that they're showing here, in real life, the nucleus is about 100,000 times smaller than the electron cloud. So if I were to really show you the size of the nucleus, I would have to take this diameter and divide it by 100,000. Well, PowerPoint doesn't let me make a dot that small, so I can't actually show you. It would be such a tiny dot that you just wouldn't even notice it. That's a big difference. What that means then is that the electrons account for most of the size of an atom. But the electrons are this hazy, cloudy distribution. So what that means is that an atom is mostly empty space. It's kind of surprising, but if you were small enough to be able to fly through an atom, it would be like flying through a dead zone. There's just not a lot going on. Now that's assuming you can ignore all the electric fields that are around you. Now when we look at the picture I showed at the first of what I found on the internet for an atom, you can see that it really doesn't make sense in terms of actual comparative sizes. These pictures are definitely not drawn to scale. In fact, you never see an atom drawn to scale because, if the nucleus is so small, it wouldn't be as pretty. It wouldn't be as interesting to look at. Another issue that we should consider is that the nucleus accounts for almost all of the mass of an atom. The electrons give it its size, what we think of as its size anyway, but almost all of the mass comes from inside that tiny point in the nucleus. That means that a nucleus has got to be incredibly dense, and it is. It's just insanely dense. So proton and neutrons, how they compare, a proton mass is about the same as a neutron mass. A neutron's a tiny bit more massive, but not enough that for our purpose we'll just say they're roughly the same. Okay, if you want to compare protons and electrons, however, proton mass is about 2,000 times more than an electron mass. Okay, so that's why the electrons really don't contribute all that much to the total mass of an atom. So think of it as the weight in that sense. Scientists have studied atoms for years, and really all of the knowledge has culminated in this, the periodic table of elements. And I guarantee you've seen this at some point in your life. So I'm not going to spend a lot of time on this. Really, this kind of discussion is the purview of a chemistry course. And we just don't have the time to really cover it with any sort of depth. So we're just going to do a quick overview and highlight some of the main points. So first of all, an element is a substance that contains only one kind of atom. Because of that, the word atom and element are often used interchangeably. When you look on the table, you can see everything is numbered. So cobalt here is number 27. If you don't remember what that means, there's a little key up here. So the number up here is called the atomic number. The atomic number gives the number of protons in the nucleus. So carbon over here at 6 means it has 6 protons in its nucleus. Oxygen has 8, so there's 2 more protons in the nucleus than carbon. I told you that the nucleus dominates the mass or the weight of the atom. And inside the nucleus we have the protons and neutrons. So if each one of these numbers, as I move up here, is adding another proton, that means I'm also adding to the total mass or the total weight of the atom. So what you can do is assume that higher atomic numbers will be more massive atoms. So at this top part of the table where we have lower numbers, these are going to be the lighter atoms. And then down here, these are going to be the heavy atoms. Up here for the lighter atoms, the number of protons is about equal to the number of neutrons. But once you start moving down to the heavier ones, you'll have more neutrons than you will protons. The reason why is a little complex, and I'm not going to go into it here. I'm not going to expect you to be able to explain it. It's an interesting fact that I wanted to point out. So as an example of the mass, lead here at 82 would be heavier than gold at 79. That means that hydrogen at 1 would be the lightest element, followed by helium at 2. These are the easiest atoms to make because they're the least complicated and require the least amount of mass. So it turns out that in the universe, these are the two most abundant elements. In fact, hydrogen strongly dominates. The universe is about 75% hydrogen. Most of the rest is helium, and that leaves not all that much for everything else. So if most of the universe is hydrogen and helium, then where do we get all of these other elements? Well, for the lighter ones, they're made in these things. So this is a photo of our sun, but in general, stars are where the elements heavier than hydrogen and helium are made. More specifically, they're made in the core, where it's extremely, extremely hot and dense, and there's a lot of pressure and temperature in order to fuse lighter elements into heavier ones. So it uses the process of nuclear fusion to make heavier elements. Now when I say heavier, there is a limit. Stars have the ability to fuse elements up to iron. And once a star hits iron, it stops being able to fuse, and that's when the star actually starts to die, we say. So eventually a star can die, and if you have the right conditions in terms of mass, you will get an extremely violent and energetic explosion known as a supernova. And it's in one of those things that the elements heavier than iron are formed. You just need more energy than a star can create on its own, so it's this sort of just extreme violent death of the star that leads to enough energy to produce all those heavier elements. If you ever take an astronomy course, you can go into this in a lot more detail. So we have a pretty decent understanding of atoms in general. Now I want to address the question, how do we see atoms? What do you think the answer is? Well, the answer is actually that we don't. We don't see atoms. So I'll explain what I mean. The guy is looking through a microscope here. This is an optical microscope, meaning it relies on light to leave the sample, enter here, and the optics will magnify the image so that it looks bigger to the observer. Okay, the key to this is the word optical. So there is no optical microscope capable of allowing a human to see an atom with their naked eye. It's not a technology issue. It's not that we just haven't created one powerful enough. It's a physics issue. There just isn't one that will allow us to do this. And again, the key is optical. So let me explain. Now, I'm going to ask, might seem like a weird question, but just go with me. It'll make sense later on. So imagine that you're stuck on this road and you've got a long way to travel. It's a really rough gravel road. Pretty well groomed, but still gravel. And it would be nice if you had some form of transportation. So you're given two options. You can ride on one of these, or you can ride on one of those. Well, obviously everybody's going to take this, the mountain bike, and there's a good reason for that. If you look at the mountain bike and you compare the tire size to the individual size of the gravel, the tire is much bigger than any individual piece on this road. So the result of that is that the tire is allowed to roll over these small objects with little resistance, and so you can get a relatively smooth ride even on a rough road like this. The skateboard, on the other hand, if you compare the wheel size to the gravel size, the wheel's not much bigger than the actual gravel, so it's going to feel every little bump, it's going to notice every little imperfection of the road, and it's really going to be a rough ride. Of course, there's issues of pressure here that we won't get into. The point is just that the interaction with the road is going to be much more intense for the skateboard, so much that it just really won't go anywhere. Right, so let's address the question then of how is it that human beings actually see anything? So if this man is looking at this tree, how does he actually see it? Well, he does it because there's light waves leaving the tree and physically entering into his eye, and then our brain interprets those light waves and gives us an image. If you didn't know, hopefully you did, light is a wave. We specifically call it an electromagnetic wave. The reason why is because there's electric fields and magnetic fields, and those are the things that are doing the waving or the oscillating. Now don't worry about fully understanding the whole electromagnetic wave issue. This isn't something I want to get into right now. It's not something we're going to test right now. I just need to bring it up so you can hopefully understand the main question that we're trying to ask is why we can't see atoms. The wave properties of light are a big reason why we can't ever see an atom with our eyes. All waves have a property known as wavelength. It's just simply the distance between two crests on the wave. There's lots of electromagnetic wave types in the world. Radio waves are an example, X-rays, gamma rays, all of these things shown here are electromagnetic waves. Human beings have the ability to sense a very small portion of all possible electromagnetic waves. We call that the visible spectrum, or just simply visible light, because this is the stuff that we can actually detect. Visible light makes up all the colors of the rainbow here. What separates red from blue down here is the wavelength, as I'm trying to show here. So if I highlight that, the distance between two peaks, you can see that the red has a longer wavelength, green is kind of a middle, and violet is the shortest of the visible light. I need to compare this wavelength distance for visible light to the size of an individual atom. If you remember, I said that an individual atom has about the diameter of an angstrom. So this is the symbol for angstrom, and what that means is it's 10 to the minus 10 meters. Or in other words, if you take a meter and divide it by 10 billion, that's an angstrom. The wavelength for light, for red specifically, is about 7,000 angstroms, meaning it's about 7,000 times longer than the diameter of an atom. That means it's really, really big compared to a single atom. Now I should point out that 7,000 angstroms in terms of human lengths is tiny, tiny. It's just that compared to atomic lengths, it's the atom is much, much, much smaller. I mean, 3 muches smaller. Green light is smaller, but not much. It's still 5,500 angstroms, and violet, as the smallest of the visible light, is still 4,000 angstroms, so still 4,000 times longer than the diameter of a single atom. Well, now's the time to bring in my whole mountain bike analogy. Trying to see an atom with visible light is like trying to fill the fine detail of the gravel road with a mountain bike. Yeah, it provides a smoother ride, but that's because it's missing all the fine detail of the gravel road. So if you want that fine detail, it turns out the mountain bike is the wrong thing to use. That's kind of like the visible light. It's so big compared to the size of an atom that any single interaction with visible light and an atom just goes unnoticed by our human eyes. We just can't pick out that small of a detail using the relatively large-scale visible light. So to explore atoms, then we really need electromagnetic waves with smaller wavelengths. They'll provide more interaction, it's just that we won't be able to see them as human beings. So it's kind of like, exploring the gravel road with the skateboard. The small diameter of the wheel, which is about the same size as the gravel, is going to give you all the detail you can stand about the gravel road. So we need the electromagnetic version of the skateboard. What we do is use special equipment that's very sensitive to smaller wavelengths than to this finer interaction. This is one example of such a machine. It's called a scanning tunneling microscope. I'm not going to go into the specifics. They're obviously not an easy machine to just understand in a few seconds. But they produce these images that look like that. Now these are false colored images. The colors are generated based on somebody's design. They don't really look pink and blue. This is an example of a single atom transistor, I believe. Here's another one that's, it's obviously a computer generated representation of what this machine is seeing. In this case, I think they had 48 iron atoms lined up in a circle. So we're just getting a computer generated representation of the data that was collected from that. So you can see it's a fascinating subject, and obviously much more complex than we're giving it credit for, but it does give us a basic overview as to why we as human beings will never be able to actually see them. But we still know a lot. We still have the ability to explore their nature, just not with our eyes. But that is a fairly short overview of Chapter 11. I didn't spend much time on it because a lot of it is a review for most people. If you've taken chemistry recently, then you know a lot about the atom already. We just don't have enough time to focus on it, where there's a lot of other physics-specific principles that are interesting as well that we want to cover.